So let's talk about each one of those steps just a little bit more. So the first step, and really a very important step in the process, is the process of pre-analysis. So before we solve things on a computer, we should really be trying to think about what we're expecting to see. So what features do you expect to see in results for this simulation that you want to do? So there's a couple different ways you can figure that out. So if you have some idea of what the governing equations will be, you can typically do either non-dimensional analysis, so you break out your Buckingham pi theorem, or sort of scaling analysis, which is a technique that I cover a little bit later in this class typically. But some way to figure out what you expect to see in the solution. An important step of this process is usually identifying whether there's a simpler version of the problem that you can solve by hand, or maybe using a different method where you can sort of cross-verify what you expect to see. So the other thing you should start thinking about before you ever really go into like a finite element analysis or a computational fluid dynamics simulation situation is whether there are ways to simplify your geometry. So are there symmetries in the geometry that you can use to reduce the problem to a simpler one? I'll talk a little bit more about that on the next slide. So some examples of pre-analysis. So at least in Meek's 640, we recently would have solved the flash diffusivity problem. So flash diffusivity is a measurement technique to measure the thermal conductivity. You have a puck of material, so where you shine light on, let's say, the top side of like this coin-shaped thing, and you watch how heat diffuses to the back side of it. You measure the temperature of the backside and use that to back out thermal properties. Well, if you're modeling that system, let's say, so as an example, what do you expect to see? What are the features of the results? Well, I expect to see that like the front side temperature will initially start hot because I dumped in heat at time equals 0. And then it'll decrease over time. The top side temperature will decrease over time because heat's going to diffuse through the material. It'll keep decreasing until there's some final value that represents the temperature being uniformly distributed over the entire coin. I expect that the backside temperature will be doing pretty much the opposite. So if I look at the backside, I expect that the temperature will go up over time, starting from 0, and then eventually stabilize out to some final value that is the steady state temperature of the entire coin. The front side and the backside temperature should be the same at that point. Meanwhile, I expect, if I'm thinking about the boundary conditions, so at least in flash diffusivity, after a little bit of pre-analysis, you can figure out that radiation and natural convection away from that little coin material is relatively negligible compared to heat redistribution within the material. And what that means is that there's effectively no heat coming in and out of the boundaries after time equals 0. So I expect to see that, let's say, the temperature gradient is pretty much 0 at the boundaries, meaning that the temperature profile is flat at either the top or the bottom for all time. I can also make an estimate of what I expect the final temperature to be. So if I dump in a certain amount of energy at time equals 0, I expect that the final temperature will represent, how much ever energy was dumped in at time equals 0 divided by the total capacitance of the sample. That's how much, I can calculate all of that ahead of time. It takes I know pretty much what to expect when I look at this solution. It's a coin cell, so even though it's a three-dimensional object that is circular with some thickness to it, I don't expect that I actually need to model that as a three-dimensional object. Unless there's like heat going out the side, I don't expect there to be any temperature gradients in that direction. So I really think that the temperature should only be a function of the depth into the material and time, and I don't really need to solve for a three-dimensional object. So there's a simplification in the symmetry of the material. Even if I wanted to model, let's say, like heat going out the sides of the material, let's say due to natural convection or whatever, if I'm trying to capture that effect, even that is an axisymmetric problem. So then it's a 2D problem. It's not a 3D problem unless there's something weird going on in like the temperature. There's some essentially like if there's nothing weird going on in the third dimension, like try to reduce the things to the lowest dimensionality that you can to do the simulation. All right, so pre-analysis helps and reduces the amount of complexity that's involved in getting a simulation result.